We looked previously at Newton's approach and the Navier-Stokes equations from an introductory point of view. Now we're going to turn to the mesoscopic scales or point of view created by Boltzmann, Ludwig Boltzmann in 1872. It could be seen as an intermediate step for the analysis of fluid motion between Newton's mesoscopic approach and Navier-Stokes macroscopic descriptions. This is more statistical fluid dynamics, even though Navier-Stokes can be seen as statistical or derived from first principles. And it describes a number, density, and number of particular microscopic particles at a time t that have position x and velocity v. This particular quantity can be represented by the probability density function f, and Boltzmann's equations for f evolving this general form in 179. The left-hand side is the free transport term, which should look really familiar. And the right-hand side are particular collision terms, written as some sort of alpha, which is usually the inverse of the mean free path of the microscopic particles, and keeps track of the collision rates. This collision operator, or the Boltzmann collision operator, on the right-hand side of 179 is a quadratic form, and it acts as a velocity variable associated with the bilinear operator. Here, omega is a deflection angle, and we've used the standard abbreviations here for 181 from Boltzmann equation. V prime 1 can be written this way with respect to omega. The collision operator can be split into a gain term and a loss term, as in 183. This loss term Q minus will count on all collisions in which a given particle of incoming velocity v will encounter another particle of velocity v1. It will change its velocity, leading to a loss of particle velocity v. This gain term, Q plus, on the other hand, measures the number of particles of outgoing velocity v, and they're created due to collisions between particles of velocities v prime and v prime 1. We shall not describe in detail the mathematical literature concerning the resolution of this Boltzmann equation, and just look at its main properties. We'll notice that for any particular test function, we'll hold this particular notation in 184. In particular, the integral of q with phi dv will be 0. For all regular f, if and only phi is a collision invariant function or combination. Multiplying the Boltzmann equation b by the collision invariance and then integrating in the velocity fields yields the formally local conservative laws of mass, momentum, and energy, e.g. the Navier-Stokes equations. This provides a link to the macroscopic description of the gas. So this is mass, momentum, energy terms, and you can see them in their form here. Another really important feature of the Boltzmann equation, as noted, comes from the symmetries of the collision operators. If we describe the integrability issues, we can choose, for example, phi is log f and find 187. This is the so-called entropy dissipation and is non-negative, and the total entropy is formally increasing. There's an error. This is the so-called Boltzmann H theorem. We call it, when we teach students in engineering, the second principle of thermodynamics, or the second law of thermodynamics. That is specifically that the entropy formally is the Lyapunov function for the Boltzmann equation, which shows that entropy must be increasing in the system of time. As to the equation, if QFF is 0 as previously stated, we can show that it's only satisfied, this inequality is only satisfied by the so-called Maxwellian distribution, which we'll call M for Maxwellian, and we'll define it here. Note the Gaussian form. Here the equation, rho is real, u is in dimensions, theta is real positive. It shows that the density is macroscopic, there's a bulk viscosity, and the temperature, theta, under some appropriate units, must be real and positive. So is density. Maxwellian distributions are therefore stationary particular states of the flow, and the entropy in particular will not decrease. It must remain the same or increase. This comes to the Cauchy problem. The whole theory is far from complete, and similar to the three-dimensional Navier-Stokes equations, it's incomplete. Global existence of weak or renormalized solutions are generally known to hold, and uniqueness of the solutions is only known in the case when the initial data is small enough and decaying sufficiently fast at infinity in velocity space, or very, very high values. This leads to a history slide on, of course, James Clerk Maxwell.